Hello guys, welcome back to my YouTube channel. Myself Kushi.D from Sri Venkateshwara College of Engineering. Today's topic is Overview Assumptions in Fault-Based Testing, which comes in software testing. So let us know what is fault-based testing. Learning objectives. Understand the basic ideas of fault-based testing. How knowledge of a fault model can be used to create useful tests and judge the quality of test cases. Understand the rationale of fault-based testing well enough to distinguish between valid and invalid uses. Understand mutation testing as one application of fault-based testing principles. Let's count marbles. A lot of marbles. Suppose we have a big bowl of marbles. How can we estimate how many? I don't want to count every marble individually. I have a bag of 100 other marbles of the same size but a different color. What I mix them? Estimating marbles. I mix 100 black marbles into the bowl. Stir well. I draw out 100 marbles at random. 20 of them are black. How many marbles were in the bowl to begin with? Estimating test suit quality. Now instead of a bowl of marbles, I have a program with bugs. I add 100 new bugs. Assume there are exactly like real bugs everywhere. I make 100 copies of my program, each one of my 100 new bugs. I run my test suite on the program with seeded bugs, and the test revealed 20 of the bugs. The other 80 program copies did not fail. What can I infer about my test suite? Basic assumptions. So these are the assumptions which we are made. We'd like to judge effectiveness of a test suite in finding real faults by measuring how well it finds seeded fake faults. Valid to the extent that the seeded bugs are representatives of real bugs, not necessarily identical. Example, black marbles are not identical to clear marbles, but the differences should not affect the selection. Example, if I mix metal ball bearings into the marbles and pull them out with a magnet, I don't learn anything about how many marbles were in the bowl. Mutation testing. A mutant is a copy of program with a mutation. A mutation is a syntactic change, a seeded bug. Example, change I less than 0 to I less than or equal to 0. Run suit on all the mutant program. A mutant is killed if fails on at least one test case. If many mutants are killed, infer that the test suite is also effective at finding real bugs. What do I need to believe? Mutation testing uses seeded faults, syntactic mutations as black marbles. Does it make sense? What must I assume? What must be true of black marble if they are to be useful in counting a bowl of pink and red marbles? Mutation testing assumptions. Competent programmer hypothesis. So this is one kind of hypothesis, that is competent programmer hypothesis. So in this, programs are nearly correct. Real faults are small variations from the correct program. Equal greater than mutants are reasonable models of real buggy programs. Next one we have here is coupling effect hypothesis. So in this, tests that find simple faults also find more complex faults. Even if mutants are not perfect representatives of real faults, a test suite that kills mutants is good at finding real faults too. Mutation operators. Syntactic change from legal program to legal program. So, specific to each programming language, C++ mutations do not work for Java and Java mutations do not work for Python. So, it's specific. Example, here we have CRP, constant for constant replacement. For instance, from x less than 5 to x less than 12, select from constants found somewhere in program text. ROR, rational operator replacement. For instance, from x less than or equal to 5 to x less than 5. VIE, variable initialization elimination. Change int x equal to 5 to int x. Scenario, live mutants, that is we have scenario, we create 100 mutants from our program, we run our test suite on all 100 mutants plus the original program. So we will run on all 100 mutants plus the original program. So the original program passes all tests, 94 mutants programs are killed, fail at least one test, 6 mutant remains alive. We can learn from the living mutants. How mutants survive. A mutant may be equivalent to original program, may be changing s like x less than 0 to x less than or equal to 0. Didn't change the output at all. The seeded fault is not really a fault. Determining whether a mutant is equivalent may be easy or hard. In the worst case, it is undecidable or the test suite could be inadequate. If the mutant could have been killed but was not, it indicates a weakness in the test suite. But adding a test case for just the mutant is a bad idea. We care about the real bugs, not the fakes. Variations on mutation. So there are two kinds of variations, that is weak mutations and statistical mutations. In the weak mutations, we have the problem statement as there are lot of mutants running each test case to completion on every mutant is expensive. Number of mutants grow with the square of program size. Approach, execute meta mutant with many seeded faults together with original program. Mark a seeded fault as killed as soon as a difference in intermediate state is found. Without waiting for program completion, restart with new mutant selection after each kill. Next we have here is statistical mutation. So in the statistical mutation, the problem what we have is there are lot of mutants. Running each test case on every mutant is expensive. It is not just too expensive to create n square mutants from program of n lines even if we don't run each test case separately to completion. What is the approach? Just create a random simple sample of mutants may be just as good for accessing test suite, provided we don't design to test case to kill particular mutants, which would be like selectively picking out black marbles anyway. In real life, fault-based testing is widely used in semiconductor manufacturing. So this fault-based testing is mainly used in semiconductor manufacturing with good fault models of typical manufacturing faults. Example, stuck at 1 for a transistor. But fault-based testing for design errors is more challenging as in software. Mutation testing is not widely used in industry but plays a role in software testing research to compare effectiveness of testing techniques. Some use of fault models to design test cases is important and widely practiced. Summary: if bugs were marbles, we could get some nice black marbles to judge the quality of test suits. Since bugs aren't marbles, mutation testing rests on some troubling assumption about seeded faults, which may not be statistically representative of real faults. Nonetheless, a model of typical or important faults is invaluable information for designing and assessing test suits. Thank you. Please do like my video if you liked it.